For most of human history, the universe seemed surprisingly honest. What you could see was what existed. The sun dominated the solar system because it was the largest object in the sky. The stars filled the night because they were really there. Galaxies glowed because they contained billions of stars. For centuries, light was our guide, and it rarely betrayed us. Every great breakthrough in astronomy followed the same pattern. Someone built a better telescope, looked a little farther, saw a little more. Again and again, the universe rewarded curiosity by revealing something that had always been there, waiting to be discovered. It was easy to believe that if our instruments became powerful enough, there would eventually be nothing left to hide. That belief shaped astronomy for generations. Then, almost without warning, it began to collapse. Not because someone discovered a new planet, not because an old theory suddenly failed, but because of a calculation. A single calculation that refused to make sense. Every scientist knows that feeling. You finish the math, stare at the answer, and immediately assume you've made a mistake. Maybe a number was copied incorrectly. Maybe an instrument wasn't calibrated properly. Maybe one tiny error slipped through unnoticed. That's how science works. Extraordinary results are never trusted the first time. They are questioned, challenged, repeated, and attacked from every possible angle. Most disappear within days. Some survive for weeks. Very few survive long enough to become genuine mysteries. This one survived for nearly a century. It survived better telescopes. It survived more precise observations. It survived entirely new generations of astronomers who wanted nothing more than to prove it wrong. Instead, every improvement made the mystery stronger. Again and again, the universe seemed to contain far more gravity than all of its visible matter could possibly produce. The stars weren't enough. The glowing clouds of gas weren't enough. Even after adding everything astronomers could observe, the numbers refused to balance. It was as if something enormous was shaping the universe, without producing a single ray of light. At first, almost nobody accepted such a conclusion. Astronomers searched for simpler answers. Perhaps there were countless faint stars that no telescope could see. Perhaps enormous clouds of cold gas were hiding between galaxies. Perhaps the calculations themselves were flawed. One by one, those explanations began to fail. And with every failed explanation, the impossible slowly became unavoidable. What if the universe wasn't missing gravity at all? What if it was missing matter, not ordinary matter, something entirely different, something invisible? Today, that mystery has become one of the greatest unsolved problems in modern science. It has inspired billion-dollar experiments, transformed cosmology, and forced physicists to question some of their deepest assumptions about reality. But before underground laboratories, before space telescopes, before decades of debate, there was only one astronomer, one calculation, and one simple conviction. He believed the numbers had to be wrong. He had no idea they would change astronomy forever. The astronomer's name was Fritz Zwicky. If you had met him in the 1930s, you probably wouldn't have guessed that he would become part of one of the greatest scientific mysteries in history. He wasn't searching for a hidden substance. He wasn't trying to rewrite the laws of physics. He wasn't even looking for a mystery. He was simply trying to answer a question that seemed almost ordinary. How heavy is a galaxy cluster? Today, that question sounds straightforward. Back then, it was one of the newest frontiers in astronomy. Only a few years earlier, scientists had realized that the Milky Way wasn't alone. The universe was filled with countless other galaxies, many of them gathered into enormous collections known as galaxy clusters. One of the largest was the Coma cluster, hundreds of galaxies spread across millions of light years, all held together by gravity. To Zwicky, it wasn't just a beautiful object in the night sky, it was a natural laboratory. If gravity was holding the cluster together, then the motion of its galaxies should reveal how much mass the cluster contained. The idea was beautifully simple. The stronger the gravity, the faster the galaxies could move without escaping. Measure their speeds, calculate the required gravity, and the mass would reveal itself. At least, that's what should have happened. When Zwicky measured the galaxies inside the Coma cluster, he found something deeply unsettling. They were moving far too fast. Fast enough that, according to every accepted equation of the time, the cluster shouldn't exist in the form he was observing. Imagine watching cars race around a circular track at impossible speeds. You know the barriers aren't strong enough to keep them on the road. By every calculation, they should fly off the track. But they don't. They continue circling as though some invisible force is holding them in place. That's exactly what Zwicky saw in the Coma cluster. The galaxies were moving so quickly that the gravity produced by all the visible stars simply wasn't enough to keep the cluster together. He checked the calculations. Then he checked them again. Nothing changed. The cluster appeared to contain far more mass than anyone could actually see. Today, we call this the missing mass problem. But in 1933, it didn't feel like the beginning of a revolution. It felt like a mistake. Zwicky himself had every reason to believe that future observations would eventually expose the error. After all, astronomy was still developing rapidly. Telescopes would become better, measurements would become more precise. The mystery would almost certainly disappear. To describe the invisible mass his equations seemed to require, Zwicky introduced a simple phrase: Dunkel Materie, dark matter, not as the name of a new particle, not as proof of an invisible substance, simply as a label, a temporary name for something that didn't yet have an explanation. It's important to understand that moment. Dark matter wasn't born as a discovery, it was born as an admission of ignorance, a way of saying, something is missing, but we don't yet know what it is. Most astronomers weren't convinced. Some questioned the measurements, others questioned the assumptions behind the calculations. Many believed that better observations would eventually solve the problem without the need for any extraordinary explanation. And for a while, it seemed they might be right. The idea quietly faded into the background. Years passed, then decades. The universe appeared to move on. But mysteries have a strange habit. Sometimes they wait patiently until someone else asks the same question in a completely different way. For decades, Fritz Zwicky's strange result sat quietly on the edge of astronomy. It wasn't forgotten, but it wasn't embraced either. Most scientists assumed the mystery would disappear as telescopes improved and observations became more precise. After all, science is full of puzzles that eventually solve themselves. A better instrument, a larger data set, a hidden source of error. History had taught astronomers to be patient. There was every reason to believe this mystery would meet the same fate. It didn't. Instead, something remarkable happened. The universe repeated itself, not once, not twice, again and again. Nearly 40 years after Zwicky's original calculation, another astronomer began studying an entirely different problem. Her name was Vera Rubin. Unlike Zwicky, Rubin wasn't looking at clusters of galaxies. She was looking inside individual galaxies themselves. Her goal seemed almost routine. She wanted to understand how stars move as they orbit the center of a galaxy. According to everything astronomers knew at the time, the result should have been predictable. The farther a star is from the galactic center, the weaker gravity becomes, and weaker gravity should mean lower orbital speeds. The solar system follows this pattern perfectly. Mercury races around the Sun. Venus moves more slowly. Earth slower still. By the time you reach Neptune, orbital speeds have dropped dramatically. It's exactly what Newton's laws predict. There was no obvious reason galaxies should behave any differently. But when Rubin and her collaborator, Kent Ford, began measuring the rotation of spiral galaxies with unprecedented precision, the universe delivered another impossible answer. The stars near the outer edges weren't slowing down. They were moving almost as fast as the stars much closer to the center. At first, the result seemed unbelievable. If the measurements were correct, it meant that the outer regions of galaxies contained far more gravity than all the visible stars could provide. Rubin did what every careful scientist would do. She questioned the data, she checked the instruments, she repeated the observations. Then she looked at another galaxy, the same result, another galaxy. Exactly the same. Another and another. Different galaxies, different distances, different sizes, different histories. The pattern never changed. Imagine walking into 10 different cities on 10 different continents and discovering that every clock is running exactly 1 hour fast. The first time, you assume it's an accident. By the 10th time, you stop blaming the clocks. You begin questioning your own assumptions. That's exactly what was happening in astronomy. Zwicky's observation had been unsettling. Rubin's observations made it impossible to dismiss. This was no longer a mystery confined to a single galaxy cluster. The same invisible influence appeared to exist throughout the universe. Different objects, different environments, different methods of observation, yet they all pointed toward the same conclusion. Something enormous was shaping galaxies, and whatever it was, light couldn't reveal it. For the first time, astronomers faced a possibility that only a few decades earlier would have sounded almost absurd. Maybe the universe we see is only a small fraction of the universe that actually exists. That idea changed everything, because once you seriously consider that possibility, every observation becomes a new question, and every galaxy becomes another crime scene. Once Vera Rubin's observations began to spread through the scientific community, the mystery could no longer be treated as an isolated anomaly. Two completely different investigations, separated by decades, had arrived at the same impossible conclusion. Fritz Zwicky had measured the motion of entire galaxies inside a galaxy cluster. Vera Rubin had measured the motion of stars inside individual galaxies. The scales couldn't have been more different, yet both pointed toward exactly the same problem. There wasn't enough visible matter. The evidence was becoming impossible to ignore. But accepting the evidence wasn't the same as accepting the explanation. Scientists are often portrayed as people who love revolutionary ideas. The reality is almost the opposite. A new theory isn't exciting, it's expensive. Every successful scientific theory represents decades, sometimes centuries, of work. It explains countless observations, supports entire fields of research, and becomes the foundation for future discoveries. Replacing it is never the first choice, it's the last. So instead of embracing the idea of invisible matter, astronomers searched for every ordinary explanation they could imagine. Perhaps galaxies contained enormous amounts of cold gas that emitted almost no light. Perhaps countless faint stars were simply too dim to detect. Perhaps dead stars, black holes, or rogue planets were contributing far more mass than anyone realized. Every possibility was investigated. Some explained a small part of the mystery. None explained all of it. It was like trying to balance a bank account that's missing $1 million by searching your couch cushions for spare change. No matter how carefully the calculations were repeated, the missing gravity remained. Year after year, paper after paper, observation after observation, the same conclusion kept returning. Something was producing gravity without revealing itself to our telescopes. Slowly, almost reluctantly, the phrase dark matter began to change its meaning. Originally, it had been little more than a placeholder, a name for an unanswered question. Now it was becoming something else, a serious scientific hypothesis. Not because anyone had seen it, no one had. Not because anyone had isolated a particle, no one had done that either, but because every alternative explanation seemed to fail. This is one of the most misunderstood moments in the entire story. People often imagine that scientists discovered dark matter and then gave it a name. The opposite is much closer to the truth. They gave the mystery a name, because they didn't know what else to call it. Imagine detectives investigating a series of crimes. At every scene, they find the same set of footprints. The footprints are real. They can be measured. They appear over and over again, but no witness has ever seen the person who made them. Eventually, the investigators begin referring to the unknown suspect by a nickname, not because they've solved the case, but because they need a way to talk about the evidence. That's exactly what dark matter became. A name for the invisible suspect, not the solution to the mystery. The solution still had to be found. And if that invisible suspect really existed, there was only one way to settle the debate. Stop looking at its effects. Find it. That simple idea would launch one of the longest, most ambitious scientific searches in modern history. Finding dark matter sounded surprisingly simple. If something invisible was holding galaxies together, then sooner or later, someone should be able to detect it. That assumption launched one of the largest scientific searches in modern history. But before anyone could build an experiment, they had to answer a much more difficult question. What exactly were they looking for? Imagine being told to search an entire forest for an animal no one has ever seen. No one can describe its size. No one knows what it eats. No one knows where it sleeps. No one can even tell you whether it has fur, feathers, or scales. The only thing anyone knows is that it leaves footprints. That was the challenge facing physicists. The footprints were everywhere. Galaxies rotated too quickly. Galaxy clusters contained too much gravity. The large-scale structure of the universe seemed to require far more matter than astronomers could observe. The evidence kept pointing towards something real. But whatever was leaving those footprints remained completely unknown. Some physicists imagined an entirely new family of particles, heavy particles that barely interacted with ordinary matter. Others proposed particles so unimaginably light that they behaved more like waves than tiny objects. Some believed the answer would emerge from powerful particle accelerators. Others argued it would be found only in deep underground laboratories. Dozens of ideas appeared, then hundreds. Each one attempted to explain the same invisible phenomenon, but despite all their disagreements, almost every physicist agreed on one crucial point. If dark matter fills the Milky Way, then Earth isn't sitting outside it. Our planet is moving through it every second. Right now, as you listen to this, Earth is orbiting the center of the galaxy at more than 200 kilometers every second. If our galaxy is surrounded by an enormous halo of dark matter, then we are constantly traveling through it. Not once a year, not once a day, every single second. That realization changed the entire strategy of the search. Scientists no longer needed to travel across the universe to find dark matter. If the theory was correct, the universe was already bringing it to us, every moment, every day, every year. Somewhere around you, right now, countless invisible particles may be passing through the room, through the walls, through your hands, through your body, without slowing down, without leaving an obvious trace. That idea sounds almost impossible to believe. Yet according to many of the leading models, dark matter interacts with ordinary matter so weakly that a single particle could pass through an entire planet without colliding with anything at all. If that were true, catching one would become one of the greatest experimental challenges humanity had ever attempted. Because finding dark matter wasn't like searching for a needle in a haystack. At least a needle eventually stops moving. Dark matter, if it exists, never does. It would pass silently through everything we know, leaving behind almost nothing except gravity. And to catch something that almost never interacts with the ordinary world, scientists would have to build instruments unlike anything ever created before. The first challenge wasn't building the detector, it was learning how to listen. The universe is anything but quiet. Every second, Earth is bombarded by particles from deep space. Invisible cosmic rays crash into our atmosphere. Natural radioactivity seeps from the rocks beneath our feet. Even the steel, copper, and glass used to build scientific instruments produce tiny signals of their own. To an ordinary experiment, none of this matters. To a dark matter detector, it's a nightmare. Imagine trying to hear a single whisper in the middle of a hurricane. That's what physicists were facing. If dark matter interacted only once in billions or even trillions of passing particles, then every other signal had to disappear, not reduced. Eliminated. That requirement forced scientists to build laboratories in places few people would ever expect. Not on mountaintops, not inside giant observatories, but deep beneath the Earth's surface, thousands of meters below solid rock. The reason wasn't to get closer to space, it was to get farther away from it. The mountain above became a natural shield, blocking most of the constant rain of cosmic particles that would otherwise overwhelm the detectors. For the first time, silence became one of the most valuable scientific tools on Earth. Inside these underground laboratories, engineers created environments unlike almost anything else built by humanity. Every material was carefully selected. Every surface was cleaned to extraordinary standards. Even microscopic traces of radioactive contamination could ruin years of work. Some detectors were filled with ultra-pure liquid xenon. Others used crystals cooled to temperatures only fractions of a degree above absolute zero. Each experiment looked different, but they all shared the same goal. Wait, not for thousands of events, not for hundreds, sometimes not even for one. A single unmistakable interaction could be enough to change physics forever. Years passed, the detectors became larger, more sensitive, more sophisticated. Each new generation promised to explore regions of nature that no experiment had ever reached before. Around the world, new collaborations formed. Hundreds of scientists became thousands. Universities joined forces with national laboratories. Governments invested hundreds of millions of dollars. It was no longer a small scientific project. It had become a global effort. From the outside, however, almost nothing seemed to happen. The detectors remained hidden underground. The laboratories stayed silent. Months passed, then years. To most people, it looked as though scientists were simply waiting. In reality, they were doing something far more difficult. They were learning to recognize the difference between a genuine discovery and a universe constantly trying to fool them, because every unexpected signal raised the same terrifying possibility. Had they finally found dark matter, or had they only discovered another way nature could imitate it? That question would define the next chapter of the search. When the first results finally arrived, they didn't come with celebration. They arrived as numbers, rows of data, graphs, statistical analyses, months of observations compressed into files that only a handful of people in the world could fully understand. For the scientists who had spent years designing, building, and operating these experiments, this was the moment everything had been leading toward. Somewhere inside that enormous mountain of data, there might be a signal unlike any that had ever been seen before, a signal that couldn't be explained by ordinary physics, a signal that would reveal the invisible matter holding galaxies together. The analysis began. Every unusual event was examined, every unexpected flash of light was questioned, every possible source of background radiation was investigated. Nothing was taken for granted, because the history of science is filled with discoveries that vanished the moment someone looked more carefully. Days turned into weeks. Weeks became months. Candidate events slowly disappeared. One was traced back to radioactive contamination. Another turned out to be an instrumental effect. Another matched a known background process that had gone unnoticed. The list became shorter, then shorter still, until finally there was nothing left. No confirmed signal, no new particle, no discovery. At first glance, it looked like failure. It wasn't. In science, a negative result is still a result. Every experiment that fails to detect dark matter eliminates another possibility. It tells physicists where the answer probably isn't. It forces theories to become more precise. It narrows the search. But there was another side to the story. Every detector had been built with hope. Hope that this would be the experiment that finally ended the mystery. And every time the answer came back empty, that hope had to wait for the next generation. Years passed, then more years. New detectors replaced old ones. They became larger, cleaner, more sensitive, capable of measuring signals that previous generations could never have observed. The search continued, and so did the silence. Entire careers unfolded between one experiment and the next. Some of the scientists who had helped launch the earliest searches retired before the mystery was solved. Others spent decades working underground, without ever seeing the discovery they had devoted their lives to finding. Yet, remarkably, almost none of them concluded that the search had been a mistake, because every unanswered question made the mystery even deeper. If dark matter wasn't appearing, it wasn't because scientists weren't looking. They had searched more carefully than ever before, which left the scientific community facing an uncomfortable possibility. Perhaps dark matter was even stranger than anyone had imagined, or perhaps they were asking the wrong question. Just as physicists began confronting that possibility, the universe produced one of the most extraordinary natural experiments ever observed. Not in a laboratory, not beneath a mountain, but hundreds of millions of light years away, where two galaxy clusters collided in deep space. For years, scientists had tried to design the perfect experiment, a detector sensitive enough to reveal something invisible, quiet enough to hear the faintest interaction, precise enough to separate an extraordinary discovery from an ordinary mistake. But while humanity was building experiments beneath mountains, the universe had already been conducting one of its own, on a scale no laboratory could ever hope to match. Hundreds of millions of light years from Earth, two enormous galaxy clusters drifted toward one another. Each cluster contained hundreds of galaxies, trillions of stars, and vast clouds of superheated gas reaching temperatures of tens of millions of degrees. For billions of years, they had traveled silently through space. Then they collided. If you've imagined a spectacular explosion, think again. Space is almost unimaginably empty. Even during a collision between galaxy clusters, the individual galaxies are so widely separated that most of them pass by each other without ever coming close to a direct impact. The stars continue on their paths, almost undisturbed. The galaxies survive. The gas does not. Unlike the stars, the enormous clouds of hot gas are spread across the space between galaxies. When the clusters met, those clouds slammed directly into one another. They slowed dramatically, compressed, heated even further, and remained near the center of the collision. Nature had done something extraordinary. It had separated the different components of a galaxy cluster. The galaxies moved ahead. The gas was left behind. For astronomers, this wasn't just another collision. It was an opportunity. Perhaps the greatest natural experiment the universe had ever performed. Because for the first time, they could ask a question that had never been possible before. If most of the mass in a galaxy cluster belongs to ordinary matter, then where should gravity be? The answer seemed obvious. Gravity should remain with the hot gas. After all, the gas contained most of the visible matter. If ordinary matter creates almost all of the gravity, the two should stay together. There was only one way to find out. Instead of looking for light, astronomers decided to map gravity itself. Not by observing gravity directly. That's impossible. Gravity cannot be photographed. It cannot be captured by a camera or reflected by a mirror, but gravity bends light. As light from galaxies far beyond the collision traveled toward Earth, the immense gravity of the cluster subtly distorted its path. The background galaxies appeared stretched, bent, slightly warped. Those tiny distortions acted like fingerprints. By measuring them with extraordinary precision, astronomers could reconstruct something no human eye had ever seen before. A map of where the mass actually was. The results stunned the scientific community. The strongest gravitational pull wasn't centered on the enormous clouds of hot gas. It remained with the galaxies that had already passed through the collision. In other words, most of the gravity appeared to be somewhere that contained far less visible matter. It was as if an invisible component of the clusters had ignored the collision entirely, passing straight through while the ordinary matter was left behind. The object became known as the bullet cluster. Even today, many physicists consider it one of the strongest pieces of evidence ever discovered in support of dark matter. Not because anyone finally saw dark matter itself, they didn't, but because for the first time, the universe appeared to separate ordinary matter from whatever else was creating so much gravity. It was an astonishing observation, one that made the mystery deeper than ever before. Because after seeing evidence this compelling, one question became impossible to ignore. If dark matter really exists, why hasn't anyone found it? At first, the bullet cluster seemed like the breakthrough scientists had been waiting for. For decades, dark matter had existed only as an explanation for strange observations. Now, many researchers believed they had found something far more convincing. Not the particle itself, but its fingerprint. Newspapers around the world called it proof. Television documentaries described it as the moment the mystery had finally been solved. To the public, the story suddenly seemed simple. The invisible matter had been found, case closed. But science doesn't work that way. One observation, no matter how remarkable, is never enough. Especially when the conclusion could reshape our understanding of the universe. Scientists immediately began asking difficult questions. Could there be another explanation? Had every possibility really been ruled out? Were there hidden assumptions inside the models? Could gravity itself behave differently under extreme conditions? Those questions weren't signs of weakness. They were signs that science was doing exactly what it is supposed to do. Every important idea must survive relentless attempts to prove it wrong. The more extraordinary the claim, the stronger the evidence must become. That's why the debate continued. Not because astronomers doubted the observations. Very few did. The bullet cluster was real. Its measurements were real. The gravitational lensing was real. The disagreement was never about what had been observed. It was about what the observations meant. Imagine arriving at the scene of a fire. Everyone agrees the building burned down. No one argues about the smoke, the collapsed walls, the melted steel. The evidence is obvious. But explaining how the fire started is a completely different question. Was it faulty wiring, lightning, arson? The evidence remains exactly the same. Only the explanation changes. That's where modern cosmology found itself. Astronomers agreed on the observations. Galaxies rotated too quickly. Galaxy clusters contained more gravity than visible matter could explain. The bullet cluster showed something extraordinary. The cosmic microwave background told a similar story. Piece after piece, the evidence seemed to point in the same direction. And yet, the central mystery remained untouched. What exactly was producing all that gravity? After nearly a century of research, scientists could describe its effects with remarkable precision. They could estimate how much of it existed, they could map where it appeared to be, they could simulate how it shaped galaxies and influenced the evolution of the universe. But they still couldn't answer the simplest question of all. What is it? That single unanswered question would eventually force some physicists to consider an idea that many believed had already been settled. Perhaps the missing ingredient wasn't invisible matter at all. Perhaps the missing piece was hidden inside gravity itself. The idea sounded almost impossible, not because it challenged a minor detail of physics, but because it questioned one of its foundations. For more than 3 centuries, gravity had been one of the greatest success stories in science. Newton's equations explained the falling of an apple and the motion of the moon using the same elegant laws. Centuries later, Einstein showed that gravity wasn't really a force at all, but the curvature of space and time itself. His theory passed every major test. It predicted the bending of starlight during a solar eclipse. It explained the strange orbit of Mercury. A century later, it even predicted gravitational waves before humanity built instruments capable of detecting them. Again and again, gravity proved itself astonishingly accurate. So when some physicists suggested that gravity itself might behave differently on the larger scales of the universe, many researchers were deeply skeptical. Why replace one of the most successful theories in history? The answer was surprisingly simple, because no one had found dark matter. Decades of increasingly sophisticated experiments had searched for it: particle accelerators, underground laboratories, ultra-sensitive detectors. Each new generation explored regions of physics that had never been tested before. Each promised to bring humanity closer to the answer, and each time, the universe remained silent. For some scientists, that silence became impossible to ignore. In the early 1980s, physicist Mordechai Milgram proposed a radical alternative. Instead of adding an invisible form of matter to the universe, what if the equations describing gravity needed to change under extremely small accelerations? Not on Earth, not inside the solar system, not where gravity is relatively strong, but at the enormous distances separating stars inside galaxies. The idea became known as modified Newtonian dynamics, or simply MOND. It wasn't an attempt to reject the evidence, it was an attempt to explain the same evidence in a completely different way. According to MOND, galaxies might not require vast amounts of invisible matter at all. Perhaps the stars weren't moving too fast. Perhaps gravity was slightly stronger than expected in environments where its pull became incredibly weak. It was a bold proposal, one that immediately divided opinion. Many physicists dismissed it, others were intrigued. Then something unexpected happened. When Milgram's equations were applied to the rotation of spiral galaxies, they worked remarkably well. In many cases, the predicted rotation curves matched observations with surprising accuracy. For supporters of MOND, this was exactly what they had hoped to see. Maybe the missing mass had never been missing. Maybe humanity had misunderstood gravity. If the story ended there, the mystery might have been solved. But once again, the universe refused to make things simple. Although MOND explained many individual galaxies surprisingly well, it struggled to explain everything else. Galaxy clusters still appeared to require additional unseen mass. The bullet cluster remained difficult to reconcile with modified gravity alone. Measurements of the cosmic microwave background strongly favored a universe containing large amounts of unseen matter. The large-scale web of galaxies stretching across billions of light years was also reproduced far more successfully by models that included dark matter. Neither side had all the answers. Dark matter explained the universe on the largest scales, but the particle itself remained undiscovered. MOND explained many galaxies with remarkable precision, but struggled to explain the universe as a whole. Nearly a century after Fritz Zwicky first noticed that something didn't add up, physics found itself in an extraordinary position. The evidence had never been stronger, the answer had never been less certain, and perhaps that uncertainty was the most important clue of all. Today, the search continues on 2 very different fronts. One looks inward, the other looks outward. Deep beneath mountains, physicists continue building detectors more sensitive than anything that came before. Every new experiment pushes the limits of engineering. Cleaner materials, lower background radiation, larger detectors, more precise measurements. The goal has never changed. Catch a single dark matter particle interacting with ordinary matter just once. One unmistakable event would transform decades of speculation into one of the greatest discoveries in scientific history. At the very same time, astronomers are searching in a completely different way. Instead of looking for dark matter itself, they're looking for the universe it should have created. Every galaxy cluster, every gravitational lens, every map of the cosmos becomes another test. Because if dark matter exists, it has been shaping the universe since almost the beginning of time. Its fingerprints should be everywhere. That is why modern telescopes have become just as important as underground laboratories. The James Webb Space Telescope wasn't designed to search for dark matter directly. Its mission is much broader, to observe the earliest galaxies ever seen. To look farther back in time than any previous telescope, to witness the young universe only a few 100 million years after the Big Bang. But every new observation becomes another piece of the puzzle. Some discoveries have surprised astronomers. A few distant galaxies appear more evolved than many scientists expected. Some structures seem to have formed earlier than certain models predicted. These observations have sparked intense discussion throughout the scientific community. Do they reveal something fundamentally new? Or will they eventually fit within our existing understanding as observations improve? Right now, no one knows. And that's exactly what makes this moment so fascinating. Contrary to what headlines often suggest, James Webb has not disproved dark matter, nor has it confirmed it. Instead, it has done what the best scientific instruments always do. It has asked better questions. Every observation narrows the possibilities. Every measurement forces theories to become more precise. Every unexpected result reminds scientists that nature is under no obligation to behave the way humans expect. For nearly 100 years, the universe has been giving us clues. Some appear to point toward invisible matter, others challenge our assumptions. Each new discovery makes the picture a little clearer, while revealing just how much remains unknown. The mystery isn't disappearing, it's becoming sharper. And perhaps that's exactly what scientific progress looks like. If history has taught us anything, it's that the universe rarely gives up its secrets all at once. Again and again, the greatest scientific discoveries have followed the same pattern. First comes an observation that doesn't fit, then years of doubt, then decades of debate, and only much later, if we're fortunate, an answer. Dark matter has followed that pattern more faithfully than almost any mystery before it. For nearly a century, every new generation of scientists has inherited the same unanswered question. Each generation has also inherited better tools, more powerful telescopes, faster computers, more sensitive detectors, and a deeper understanding of the universe than anyone before them. Yet the mystery remains. That isn't a sign of failure. It's a reminder of how little of the universe we truly understand. Consider this for a moment. Everything you've ever seen, every star in the night sky, every planet, every cloud of gas, every black hole, every galaxy, all of it appears to account for only a small fraction of the total matter believed to exist in the universe. If our current understanding is correct, then everything familiar, everything that makes up people, planets, oceans, trees, and stars, is only a minority of the cosmic story. Whether the missing majority turns out to be an undiscovered particle, a deeper theory of gravity, or something no one has imagined yet. The implications are enormous. Every major technological revolution in history began with a deeper understanding of nature. Electricity was once an invisible curiosity. Quantum mechanics seemed like an abstract mathematical puzzle. General relativity appeared to have no practical application. Today, those discoveries shape almost every aspect of modern civilization. No one can predict what understanding dark matter, or replacing the idea entirely, might eventually lead to. History suggests only one thing. When humanity uncovers a deeper layer of reality, the consequences are rarely confined to textbooks. But perhaps the most remarkable part of this story isn't what we know. It's what we're willing to admit we don't know. Science isn't powerful because it always has the right answers. Science is powerful because it's willing to abandon even its most cherished ideas when the evidence demands it. That's an incredibly difficult thing to do. It requires patience, humility, and the courage to say three simple words. We don't know. Those words aren't the end of science. They're the beginning of every great discovery. That's why physicists continue searching. Not because they're certain dark matter exists, not because they're convinced gravity must be wrong, but because the universe has presented humanity with a mystery that refuses to disappear. And history has shown that mysteries like this are usually trying to teach us something profound. Whatever the answer ultimately turns out to be, it will change the way we see the universe, perhaps even the way we see ourselves. Because every time humanity has looked deeper into the cosmos, the universe has revealed something completely unexpected. There is every reason to believe it hasn't finished surprising us yet. When this story began, astronomers believed they understood one simple rule. If you can see all the matter, you can explain all the gravity. That assumption seemed almost impossible to question. It survived generations of discoveries. It survived the birth of modern physics. It survived the arrival of Einstein. Then the universe quietly presented a contradiction, not through a spectacular explosion, not through an object unlike anything ever seen before, but through numbers. Numbers that refused to agree with everything humanity thought it knew. For almost a century, those numbers have remained. The names of the telescopes have changed, the computers have changed, the scientists themselves have changed, the mystery has not. Today, somewhere beneath mountains, detectors continue listening for an interaction that may never come. Above Earth's atmosphere, telescopes continue mapping galaxies farther away than anyone once believed possible. Supercomputers simulate entire universes, comparing theory with observation in extraordinary detail. Every year, another piece of the puzzle falls into place. Every year, another question appears. Perhaps tomorrow, one detector will record an event unlike anything ever seen before. Independent laboratories will confirm it. Scientists around the world will repeat the analysis. Months later, the announcement will finally come. Humanity has discovered the particle responsible for dark matter. If that day arrives, it will instantly become one of the greatest discoveries in scientific history. It would reveal a completely new component of nature, one that has shaped galaxies since the universe was young, yet remained hidden for billions of years. But there is another possibility, one that is just as extraordinary. Imagine another 20 years pass, then another 20. The detectors become even larger, the telescopes become even more powerful. Artificial intelligence analyzes more data than any human could examine in a lifetime. And still, nothing. That outcome wouldn't simply delay the answer. It would force physicists to ask a question far more profound than the one that began this story. What if nature has been trying to tell us something entirely different? What if the greatest discovery isn't a new particle, but a new understanding of gravity itself? At this moment, no one can honestly say which future awaits us, and that's what makes this period in scientific history so remarkable. We're not reading about a mystery that was solved generations ago. We're living through it. For the first time, humanity possesses instruments sensitive enough to test ideas that once belonged only to philosophy. For the first time, we may be close enough to discover whether most of the universe is invisible, or whether our understanding of reality is still incomplete. Whatever the answer turns out to be, future generations will read about this era in history books. They will know how the story ends. We don't. And perhaps that's the greatest privilege of all. We are alive at the moment when one of the oldest questions ever asked about the universe is finally within reach. Perhaps the most surprising part of this story isn't that we haven't found the answer, it's that the universe never promised us one. For centuries, every major scientific breakthrough has changed the way humanity sees itself. Copernicus showed that Earth wasn't the center of the universe. Darwin showed that humanity wasn't separate from nature. Einstein showed that space and time were not the fixed stage we once imagined. Every one of those discoveries forced us to give up something we believed was obvious. Dark matter, or whatever ultimately explains this mystery, may demand exactly the same thing. Because this has never been a story about an invisible particle. It's a story about the limits of human understanding. We often imagine science as a collection of facts. In reality, it's something far more remarkable. It's a process of gradually replacing certainty with better questions. Every answer opens the door to another mystery. Every discovery reveals a deeper layer of reality. The universe doesn't become simpler, our questions become better. That's why scientists continue searching, even after decades without a definitive answer. Not because they're stubborn, not because they've invested too much to stop, but because the evidence refuses to disappear. The galaxies still rotate too quickly. Gravity still appears stronger than visible matter can explain. The oldest light in the universe still carries the same message. The clues continue pointing towards something we don't yet understand. Whether that something turns out to be a new particle, a deeper theory of gravity, or an idea no one has imagined yet, the search itself has already transformed science. It has driven the development of detectors so sensitive they can measure events once thought impossible. It has inspired new telescopes capable of looking farther into the universe than any previous generation could dream. It has united astronomers, particle physicists, engineers, mathematicians, and computer scientists in pursuit of a single question. That is one of the remarkable things about science. Even before it finds the answer, the search changes the world. Perhaps one day, someone will look back at this period the way we now look back at the search for gravitational waves or the discovery of the Higgs boson. What feels uncertain today will seem inevitable in hindsight. History has a way of making difficult discoveries appear obvious after they've been made. But they never feel obvious while they're happening. Right now, we are standing in that uncertain moment. A moment between question and answer, between evidence and understanding, between mystery and discovery. And someday, whether it's next year or 50 years from now, someone will take the final piece of this puzzle and place it where it belongs. When that happens, humanity won't simply learn something new about the universe, we'll learn something new about reality itself. Until then. The greatest mystery in modern cosmology remains exactly what it has always been. Not a problem waiting to disappear, but an invitation to keep exploring. Because the history of science has taught us one lesson above all others: the universe is always stranger than our first explanation. And that's precisely why it's worth trying to understand.